Hi, everybody. In this lecture, we're going to finally start talking about phase transitions. Now, phase transitions are something that you're intimately familiar with from existing in the world. You've seen water boil and become steam. You've seen water freeze and become ice. And you may have even seen more exotic phase transitions out there in reality. Phase transitions come to us in the theory of classical thermodynamics seemingly as a little bit of a technicality. And actually, it occurs in two ways. The first is that we assumed when we were maximizing the entropy, so we have our entropy, for instance, as a function of UVN, and when we do some sort of a join, we assume that we are maximizing this entropy subject to, let's for instance talk about a thermomechanical join. So U1 plus U2 uh, is constant, and V1 plus V2 is constant. And we found that a helpful object in considering this sort of constrained maximization problem was the partial with respect to V of S for either system while fixing U and N, which we saw was P over T. Okay, well, fair enough. The reason that this ended up being helpful was because it helped us determine where the point that maximized this equation was. Another thing that we have been assuming, especially as we've been talking about Legendre transforms, is that the function that we're Legendre transforming is everywhere concave up. So we have our x-axis, our f-axis, and we have some sort of function here that is everywhere concave up. And we've gone to some length to show that at least for some p, for some domain, this will always have a minimum. In particular, we've shown that any extreme point will be a minimum. Okay, so it turns out that by relaxing the assumption that this is concave up, or by relaxing the idea that this equation has exactly one solution, we get phase transitions for free. So what seems like a technicality in the math, just something that comes out of the calculus about these functions, has all of these consequences in the world that we actually see. I'm going to motivate this all with an example, but first I'm going to need to clean up the board. I'll see you in just a second. Okay, welcome back. Down here in this free space, I want to quickly work out what is the Helmholtz free energy for the ideal gas. So we have Helmholtz free energy is F is equal to U minus TS, and the natural coordinates are T, V, and N. So let's do this for the ideal gas. We'll get that F is, so let me point out, this is for the ideal gas. So we'll get F is 3/2 NkBT minus T times S, which is NkB, log of sigma V over N. And then U over N I'll rewrite as 3/2 NkB over N. But that's just 3/2 times KBT. Sorry, I should have said 3/2 NkBT over N. So that's 3/2 KBT. Then this is raised to the 3/2. We close it. And then we would also have plus 5/2 NkBT. But because of the attachment to minus t, we also just get a minus 5/2 NkBT. Now you'll notice that we can clean this up in a couple of ways. The 3/2 and the 5/2 cancel down to just a -1. And then this can be reconfigured back into NKBT. So our result for the ideal gas, I'll write right up here, is F is equal to, well, I'm going to factor an NKBT out. Then we get -1 minus log of, or maybe I'll just factor out an overall minus sign. Okay, so then this becomes just 1 plus log of sigma V over N 3/2 KBT, sorry, to the 3/2. Close that, good. And this is the free energy for the Helmholtz free energy, I should say, for the ideal gas. Now, we want to look at a slightly different equation of state for a slightly different gas system. In fact, this is our first non-ideal gas system that we're going to look at in detail. It's called the van der Waals gas. I hope someone someday will correct me on my Dutch pronunciation here, because I'd really like to hear how this should actually be pronounced. But in any case, it turns out that this describes a gas system where we think of the gas particles as taking up some non-zero volume and where they have some small repulsive interactions with each other as well. We'll get to that, why any of this would matter, a bit later in the course, but for now, let me just write this down. So we still have minus NKBT, then 1 plus log sigma. Now this V is going to be replaced by V minus NB. Notice that B is intensive and of type volume. It represents basically the volume of each individual gas particle. Good, then we'll divide that by N. Okay, then 3/2 KBT to the 3/2, just as before. Close that. And then we're going to subtract another term, A times N squared over V. Good. Okay, so, and I should have said, this term describes somehow this repulsive interaction between the gas particles. So our goal now is to try to figure out the Gibbs free energy. So goal, figure out G, Gibbs free energy. Well, how would we do that? Let's first try a naive approach. Missing a color. Interesting. Let's first try a naive approach. So remember that G is, in fact, a Legendre transform of F. So G is equal to U minus TS plus PV. Or is equal to, since all of this is F, F plus PV. So in principle, all we need to do is find P for this system, then we can plug it in to find G. So naive approach, okay, so I'm going to define what we would typically think of as the pressure, but I'm going to call it P super naught, just to sort of hint at the fact that this might actually not be exactly what it seems. Okay, so as usual, this would just be T times the partial with respect to V of F, while fixing T and N. And if you're not familiar with that, let me just write the thermodynamic identity for F, which you will have seen before. So dF is minus S dt minus P dV plus mu dN. Okay, good. So, oh, and there should be a minus sign in here, because of this minus sign here. Okay, so let's do it. This will give us some practice with taking derivatives. So we want to take the derivative of that equation with respect to v. All right, let's get to it. So P naught is equal to minus t times, the first place that v appears here is right here. In fact, this is the only place that it appears. So minus nkbt times 1 does not affect this derivative, but we do get a minus n. And I'm realizing that this t actually should not be here either. Oops. The thermodynamic identity suggests that p just is this partial derivative. Good. The astute among you will have noticed that my type didn't work out right on the two sides of the equation. Okay, so get rid of this minus t. Instead, we just have a minus sign, and then we'll pull out our minus nkbt. Then we take the derivative of the log. V is just shifted here by a constant factor, so the chain rule won't give us anything. Instead, we'll just get 1 over this object, v minus nb, since this was not raised to any power. Good. Then we'll need to take into account this term. So here we have an squared v to the negative 1. If we take a v derivative of v to the minus 1, we'll get v to the minus 2, but also a net minus sign. So we'll get plus an squared over v squared. Good. Okay, let's slightly rewrite this. So P naught, P naught is equal to nkbt over v minus nb, and then a minus sign here, an squared over v squared. Excellent. Notice how similar this is to the ideal gas law. So for the ideal gas, A would have been 0, and B would have been 0. And so this would, in fact, reduce to exactly the ideal gas. And we wouldn't have had any sort of v squared dependence here. I think a pretty reasonable thing to do would be to clear denominators here. So let's do it. Then we'll get P naught times v squared times v minus nb is equal to nkbt times v squared minus an squared v minus nb. And notice that because we have a v squared multiplied by v here, this is a cubic polynomial equation. So whereas before we had a nice linear relationship, PV is equal to nkbt, here we have a much more complicated cubic relationship. And there's a problem with cubic relationships like this, namely that they don't necessarily have one solution. I'm going to clean up the board and we're going to start drawing what we think this relationship should look like. Okay, I've copied our equation from the last board over here. And now we also have this figure that I'm in the process of constructing. We have volume on our x-axis, and we have pressure on our y-axis. And notice that I've put an asymptote at V equals NB. In fact, the state space for the van der Waals gas is only going to include states that have V greater than NB. The physical reason for this is that we know that each particle has volume B, so we can't have the system have less than the total volume of all of the particles. And then the sort of more, I don't know, maybe mathematically motivated reason is that the equation turns out to not make sense. You'll get a negative inside of the log if V is less than NB. Okay, all of that aside, this equation is going to be, I should say, this equation can be plotted in these in these coordinates. And since we care about fixed t and n, let's look at the solution for different values of t. Okay, so we basically get three types of behavior. The first type involves something like this. The second type involves something like this. And the third type involves something like this. All right. This is what we get at high temperature. This is what we get at low temperature. And this is what we get at some critical temperature. I'll put that in quotation marks since we haven't really defined what it means yet. This figure now shows us our big problem. We had that f was a function of tvn, and we want to move to g, which is a function of tpn. That means we need to take our solution, p naught, as a function of v, and turn it into a solution v as a function of p. But we can't always do that, precisely because in this range, this graph will not be invertible. So in here, we have a problem. The question is, if we think again of G as the V Legendre transform, what we actually want to do is find the minimum. So again, G of P is equal to the minimum over V of F of V plus PV. And yeah, everything matches. Good. But this might not unique, so there might not be one solution. So in this case, there is possibly more than one solution to f prime of v is equal to minus p. Good. Notice that I've suppressed the dependence on t and n just for the sake of clarity here. Okay, so this is exactly the problem that we had when we were taking the Legendre transform of a function that wasn't concave up, which if you try to plot it out here, take f as a function of v, you'll see is the case for us in this example. So that's the problem, laid out really bare. We might have two possible solutions to this, and we'll have to compare them we might have two solutions to this equation, and we'll have to compare them to see which one actually minimizes this expression. Whichever one does minimize this expression gives us G, and more importantly, tells us what the actually achieved pressure is. So the system will achieve one of several pressures at a given volume, and we need to figure out which one it will be. Sorry, the system will achieve one of several volumes at a given pressure, and we need to figure out which it will be. So if we started at a volume, or sorry, at a pressure like this, or I should say, if we set a pressure like this, we know the system would achieve either this volume, or this volume, but it's not clear which one. I'll leave us off by just stating that in fact it isn't this one. The reason is that as we look to take the Legendre transform, this will turn out not to be a minimum. So it will be one of these two. In the next video, we'll get to the strategy to figure out how to exactly fix this problem and choose which volume is achieved at a given pressure P. Thank you so much for watching, and I'll see you in the next one.